particularly for turfgrass trials, we had my former student now, Amninder Singh, who is a postdoc right now, and then Jean-Claude, who will be talking. He'll be talking during this presentation after I'm done talking about previous projects. He's going to talk about his project. He is a PhD student in my group. And Maggie, who was an extension educator at UCR, and Darren Haber. So we had quite a few trials in, again, Central California, Orange County, and Riverside. And I'm not promoting by any means turfgrass. I mean, we are just generating science-based information. In fact, we have 16 species right now. 2 of them are turfgrass. The rest are alternative ground cover species. But I think there is a need to develop science-based information for turfgrass. They are providing benefit to society, and then that's what we are doing in my research group. So just a brief history of the work that we had done in the past. In 2016, when I joined UCR, we started actually building some infrastructure in Riverside for turfgrass irrigation. So the first trials we started in 2017, 3 years data collection for hybrid Bermuda grass, which is a warm season turfgrass, and tall fescue, a cool season turfgrass that is basically requires less water than the other cool season species. And it was an evapotranspiration study. So we did all the irrigation management based on the evapotranspiration, okay? And then we kind of did a similar study up in UCR Kearney in Central California, the exact same species, and the objective were the same. What is this water saving potential? Can we actually use smart evapotranspiration or weather-based controllers to regulate deficit irrigation to save water? And after 3 years, we changed the species. Right now, the background picture that you see are actually tall fescue and hybrid Bermuda grass. But right now we have here buffalo grass and St. Augustine grass. That these are the trials that Jean-Claude is managing. So he's going to talk about these, going to share some preliminary results and talk about his study soon. At the same time, at 2017, when I started, we also looked into smart soil moisture-based controllers. So we had a trial in UC Riverside. We used tall fescue, and we used 4 or 5 different soil moisture-based controllers. How they worked, what is their efficiency? Are they reliable, ease of use, and things like that. And also we had a trial in Orange County, actually, in the South Coast Research and Extension Center that Janet mentioned. It was a hybrid Bermuda grass using soil moisture-based irrigation controller, and we just finished that last year. So the difference, of course, between these cities are climate, soil type, and also in South Coast, we use recycled water for irrigation. So salinity and salinity buildup was also a question that we wanted to ask. If I want to talk about the results of this work in details, it's going to be a couple of hours. So I'm just going to highlight few things that I think are we learned over these years. There are still a lot of data that we given a chance to analyze them. So the way that research works and research-based information is being produced is that we repeat the measurements and everything over time and in a space, because we want to minimize error, and we want to basically rule out the randomness and then get those results that are reliable and we can share. So that is why you can see that it's a very time-consuming process, 3 to 4 years every time that we want to run a field trial. So the first, of course, and foremost, we wanted to know whether there is water conservation potential of these turfgrass species. Actually, I was very optimistic that we could maybe cut the water back by 20–30%. Generally, we didn't see that. So that 80%, 60%, 80% for tall fescue, 60% for, for cool season, and 60% for warm season. We actually ended up applying more water. And some of that water was, of course, water lost, although we followed all the best management practices, irrigating over time, having soaking enough time for soak and cycle and everything that is recommended, but I'm sure there has been water loss. But the turfgrass didn't show the water saving potential that I expected to see, or I hope to see. So I think that's the first thing that I wanted to point out. And then there is literature coming from other colleagues who are turf specialists and work that is being done in greenhouses. They get better results. Maybe part of it is because we were doing some relatively speaking bigger plots out in the field. So if you control everything in small pots in greenhouse, maybe you get better results. One thing that we realized is that you can stress turfgrass, you can cut the water back, but depending on how much water you apply and depending of the demand, evaporative demand. So if it's a hot summer and the evaporative demand is high, then you have 1 month, 2 months, 3 months, again, we have published these results, until you get to a point that the turf quality is not acceptable. So it's possible to stress them to save water, but it's not going to be for 6, 7 months. It's going to be 2 to 3 months, and then we need to refill the soil profile back again. One thing that we realized, and then you see this message in my talks, Janet, and all my students, and also Don, about talking about urban heat islands. So this is something that we measured. We actually started with water conservation as the main goal, but then we soon started collecting temperature of these turf plots. So what is that trade-off between water, conserving water and still having the cooling benefits? One thing, just I don't have the detailed data here. In that Kearney trial in Central California, we saw 30 to 35 degree Fahrenheit higher temperature from dead turf compared to irrigated plots on average. So just to have some numbers in your mind, some ideas about how significant the cooling benefit would be and how significant the temperature differences are. Another question was about these policies that the municipalities impose, and Janet mentioned that during the drought, they say, okay, restrict watering days. 1 day a week, which I think is a little bit tricky to apply water in only 1 day. And then sometimes 3 days, 4 days. So we wanted to know if there is water saving potential. And remember, we are scheduling everything scientifically. So if somebody is wasting a lot of water, perhaps limiting watering days would help. But we didn't see that in our plots. In fact, what I call on-demand irrigation, which basically we let the controller to choose the watering days based on the evaporative demand of the atmosphere was the best in terms of keeping the turf healthy. The tricky part about 1 day per week irrigation is that if you want to apply so much water so fast to make up for that 7 days of not irrigating 6 days, then the chance of runoff and deep percolation would be high, especially for our sandy soil. So that's something that we don't want to happen. In fact, we are working on a project with another colleague of mine. I'm not going to share the results, and Jean-Claude is doing that. We are going to look into the implementation of these policies, restricting watering days in Southern California, using historical water applications at regional level. How successful these programs were? Do we see any spike in temperature and urban heat island? Do we see any neighborhood and disproportionate, any neighborhood and any demographic that was impacted disproportionately? So that's something that we have been thinking about it, and we're going to do it using satellite images, remote sensing. How smart controllers performed? Weather-based controller that we use with on-site weather sensor. We saw over and over that they are 5 to 10% different than CIMIS, which is the reference that has all the sensors. So these are coming only with the temperature sensor, but they are reliable. And we are using Weathermatic smart controllers. So it's really important that when you want to promote the smart controllers or use them, use the ones that they have been tested in scientific community. There are ones that are called smart, but they are not really science-based. So, and then we saw some inconsistency when we used soil moisture-based control, soil moisture sensor-based with recycled water. We still need to look into that. One hypothesis that we have is that salinity actually had an impact, negative impact on that. So again, we started with water conservation. Soon we added temperature and cooling benefits. So we are now looking at that trade-off. And then Jean-Claude, actually, since he started last year, he added another component that is very important, greenhouse gas emissions. So the irrigation practices that we have, how much they contribute to basically CO2 or carbon dioxide emission, or maybe even capturing carbon dioxide. Do we see any significant differences based on the irrigation frequency, irrigation application rate? And that's something that we are going to bring it. So we have when we want to think about irrigation management, so we not only think about water conservation, but also urban heat island and greenhouse gas emission. Two more take-home messages. One is that I mentioned this before. Yes, turfgrass can withstand period of water stress before the quality falls below the minimum acceptable threshold. So people who have turfs in residential areas, other areas, if the water conservation is really required, they can stress the turf. What happens is that turf start using the water that is within the soil profile, and then depending on the type of turfgrass, they are going to show signs and symptoms of drought injury after a couple of months usually. And then deficit irrigation, of course, is good to save water, but there will be a spike in temperature, and we will show more data on spikes in temperature in the future presentations by my students. And then this is also maybe a general overview of, there was a question about water conservation. If we don't have smart controllers, how to conserve water. So I'm going to talk about that for a minute or two. So the objective of our group, the main objective, all the projects that we do, I would say, is water conservation. Choosing the right plant type is one solution or strategy, but we have so many other things that we can do. So you choosing or identifying plants that are drought and heat tolerant, it's good. But we also need science-based information or reliable information about how much water they need. So if it's not enough that we think or we believe that they need less water, we need to know exactly how much water they need, and or how, when we stress them, we give them less than they optimally need. What's going to happen to them? Are they going to die, or are they going to slowly growth, and or the mechanisms that Don articulated in his presentations are going to happen? Another thing that is maybe low-hanging fruit, honestly, is to enhance irrigation efficiency. So even if we know how much water plant type needs, and then we know how much stress we can impose, the water that we apply, only that portion that is being used by the crop is the beneficial use. The rest is waste. So runoff, deep percolation, evaporative loss, wind drift. So we can avoid all of those that with just using best management practices for irrigation, irrigating overnight, having soak and cycle, not irrigating too long that cause runoff, looking at this distribution uniformity of a sprinkler heads, fixing broken or tilted sprinkler heads, zoning when it's required. And another topic that I'm going to talk briefly is that enhancing rainfall use efficiency. We keep talking about irrigation, but we get some rainfall during the rainy season. If we have compacted soil, the rainfall would be mainly runoff. If we are irrigating over the rainfall, then that would be a waste of water. So we need to kind of bring that rainfall into, take it into account. Don't over irrigate or irrigate when we receive enough rain. And also make sure that the soil can actually hold that rain, and then infiltration is high. And that's a topic that would be the topic of last presentation by my students. They are going to talk about the case study in UCR Botanic Garden, but I want you to look at it as an very important factor in terms of avoiding runoff and increasing infiltration, and the negative impact of soil compaction, which we see in so many settings in urban areas. All right, with that, again, Janet mentioned that .com websites are not reliable. This one is an exception. This is my research website, ucrwater.com. You can email me if you had any question. And I'm going to stop here. Jean-Claude, if you're there, you can start sharing your slides and talk about your work.
Thanks, Amir. Amir, you have a couple minutes. Do you want to take any questions? I don't see any in there.
No, we haven't finished, Janet. John Claude, my student, is going to talk about the remaining.
Okay, right. I didn't know whether after your talk you wanted to take a question or two.
Oh, yes, yeah, sure. If there is a question, I will have time.
Yeah, anything for Amir? It's 11:02, so you actually have 3 more minutes. So going. And you can add it all up. You got the rest of the time, Amir, with these talks. So if you want to just have the questions at the end of all your groups, that's fine too.
Thank you.
Okay.
All right, Jean-Claude, we can see your slides. You're muted. If you unmute yourself.
All right. Can you hear me?
Yes. Go ahead.
All right. Good morning, everyone. I guess I'm going to talk about the impact of irrigation rate and frequency on turfgrass performance. And I will just try to go first, since many of the informations have already been discussed in the previous presentations. Just to start, this background photo kind of shows what I've been talking about urban heat island, which is basically shows how, like, in urban centers, we have more temperature than in suburban areas where we have more vegetation cover. But another important thing that I wanted to mention is that urban lawn or turfgrass constitute around 68% of urban greeneries. So one of the major the performance, like the performance of this greeneries, like urban lawn, has much impact on what's going on here. So besides cooling down, also the plants helps to capture carbon dioxide, as I mentioned. But we are seeing the changes in irrigation because like in California, we are restricting how much and how often to irrigate. And we really want to know what's going on. How is this going to impact the turfgrass? In the previous research, people have been focusing on looking at the turfgrass quality. But in this study, we want to look at 3 main aspects. We want to look at the turfgrass quality, which is very important as aesthetic value, but also want to look at the cooling effect of the turfgrass. And we also want to look for the carbon capturing or carbon sequestration of turfgrass. And we want to analyze how does the change in irrigation is going to impact all these 3 parameters. And the ultimate goal will be to see if we can identify the irrigation rate that can help us cool down the canopy, save water, and also contribute to capturing more carbon, since now one of the major problems we have is higher concentration of greenhouse gases. But to do that, we are focusing on 2 warm season turfgrass, buffer grass, and St. Augustine grass. Again, we choose warm season because in California, like, we need more like plant species that use less water. So that's why we're focusing on warm season. And we're using ET-based mud controller. Like, again, like mentioned, it can help automate irrigation and estimate how much to irrigate. And we are applying different irrigation levels, which are based on percent evapotranspiration. The highest is 80% and the lowest is 30%. And we're applying 2 different irrigation frequencies. We apply 3 days to kind of represent where there's irrigation restriction in terms of frequency. And we apply 6-day irrigation frequency as to represent where there's no restriction on how often to irrigate. We are collecting different data, such as carbon dioxide flux, which is pretty much how much carbon is going is emitted from the soil through respiration. And we are collecting soil moisture and temperature. We collect canopy temperature and canopy greenness, which is indicated by normalized difference vegetation index, which is basically shows how green the plant is, and where we see in the results where 0 indicate like a dead plant and 1 could be like a great healthy, but for turfgrass normally around 5 to 6 indicates a healthy plant. And also measure air temperature and relative humidity. like I mentioned, on the left, you see what's normally like carbon dynamics in turfgrass. So carbon can be captured through photosynthesis, but it can also be lost through respiration of roots or microbes in the soil. And also, we can lose more carbon or contribute to emission when we use few-powered mowing machines, or through fertigation and other sources of emissions. So all these ecosystem, we want to see how irrigation is going to impact this. Will irrigating less frequent contribute more to the loss or to the more capture? And we want to not only look at the emitted, but also want to look at the net carbon. So we measure how much carbon is left in the soil after the growing season and how much is stored in the biomass, because plant can also store carbon in the plant tissues. And also we account for the carbon lost, what they call hidden carbon cost, which such as the carbon lost through mowing. When we use few-powered mowing, we emit carbon, and that we put that into consideration to measure the net carbon. And we also measure how much carbon can be emitted through irrigation or other management practices. Since monitoring plant growth really takes time, we are trying to incorporate new technologies that can save time and help us to monitor more efficiently. So we use a drone to develop methods of monitoring turfgrass, where we measure land surface temperature and normalize different vegetation index, again, which can tell us more about the plant health. So on these two pictures kind of highlights the first year, at the end of the first year of data, how the plant looks like. So on the left, you can see a healthy buffer grass, which has an NDVI of 0.5, again, which is acceptable for turfgrass, and the temperature, canopy temperature of around 98. And on the right, you see another buffer grass, but irrigated by 30%. And you can see that it has higher temperature and low NDVI, which is low quality. And these four graphs kind of highlights the preliminary results. So we can't make any conclusion right now. We're just going to explain the general trend as so far. And you can see that reducing the rate kind of help us to save water. So on the y-axis is its volume of water applied, and the x-axis you see irrigation rate. And you see the purple color is 6 days and blue color is 3 days. And you see that there is a general trend as we reduce the rate. Also on the canopy quality, our NDVI values, you can see that there is a general declining trend as we apply the rate. However, you can see that for the first 3 rates, like to reach at 60% evapotranspiration, you can see that there isn't really significant difference, but you can see that here there is a little bit lower compared to the 3. Again, on the canopy temperature, you can see that there is a general increasing trend when we reduce the amount of, when we reduce the rate of irrigation, the canopy temperature also increases. And for the CO2 flags, again, I would say there's a general declining trend of CO2 emitted. And this one is, the study is still early stages, so we can't make any conclusion, but so far this is kind of to give you an idea of what you're trying to analyze. So again, the goal is to look at using these 4 informations to look at the rate that can help us save water, give us acceptable quality, and can lower canopy temperature and average, like help us reduce the carbon dioxide loss through respiration. As a take-home message, I guess in addition to providing aesthetic value, many people see turfgrass as just like leisure. You just value for playing golf. Turfgrass can also help minimize urban heat and also capture carbon dioxide. And it can also give us these 2 ecosystem services. And another thing is that how much and how often we irrigate matters. So when we change how much and how often we irrigate, it's really impacting the plant physiology and the plant performance. And as Dr. Habadi mentioned, investing in smart controllers can help us, can ease the way we estimate how much we irrigate, also improve irrigation efficiency. And this is the acknowledgement, Dr. Hagvaldi and my colleague Anish and Zara, and UCR Agriculture Operations. Thanks.
Thank you, Jean-Claude. We are running behind. So Anish, why don't you share your slides and we can answer questions at the end.
Can you see my screen?
Yes, I can see.